Hello, welcome back to week 4. Today we're going to talk about specific internal energy and enthalpy. Okay, so first one is internal energy. We all know what internal energy is because we've been using it for a long time with first law. Internal energy. We use capital U for internal energy, and just like any other energy, the SI unit is joule. And usually sometimes we use kilojoule for engineers. And then after that, we also introduced specific internal energy. Specific means per unit mass. So the definition is total energy divided by mass. And we use lowercase u for specific internal energy. And the unit for specific internal energy is joule per kilogram, which is the SI unit, or kilojoule per kilogram. Okay, so that's something we already know. And today we introduce a new one. We introduced a new concept, a new property. It's called enthalpy. Enthalpy is another format of energy which we will use a lot when we move on to control volume after we finish closed systems. Okay, we use letter H. We use letter capital H for enthalpy. And then, just like any other energy, the unit is joule, which is SI, and engineers usually use kilojoule. Okay, so now what's the definition of enthalpy? The definition of enthalpy, capital H, is equal to internal energy plus PV. Capital U is internal energy. And what is P? P here is pressure. And V here is volume. Be careful because V here does not stand for velocity. V here is volume. Okay, and then just like internal energy, we also have per unit, so we call it specific enthalpy. Specific enthalpy. Okay, specific means per unit mass, so the definition is capital H, total enthalpy, divided by mass, and we use lowercase h for specific enthalpy. Okay, so now we can continue. We can plug in the definition of capital H. The definition of capital H is internal energy, capital U, plus pressure multiplied by volume divided by mass. And then we can continue. The first term is capital U over m. Capital U over m is lowercase u. Plus the second term, you can keep pressure, and then what is left is volume over mass. Volume over mass is specific volume, which we call nu. U plus P nu. That's specific enthalpy. The unit for specific enthalpy is joule per kilogram, which is SI unit, or kilojoule per kilogram. Both are correct. Okay, so the next part is how do we look for those properties? Internal energy, enthalpy, specific internal energy, specific enthalpy. There are properties, and how do we look for properties? We can still find them from the table. Next one, retrieving specific internal energy and specific enthalpy with the tables. We've used the table before to look for specific volume nu, and we can use the table too to look for specific internal energy U and a specific enthalpy H. Okay, and then what if you have A mixture, remember? How do you look for the nu of a mixture? Do you remember the equation? If you understand it, you can memorize it very easily. If you have a mixture, and then the nu can be calculated from this equation. First of all, your mixture will have two components. The first component is saturated liquid, point F. The second component is saturated vapor, component G. And then how much do we have for each one of them? How much we have for vapor is the definition of quality, so that's X. And how much do we have for the liquid? That's the rest, so it's 1 minus X. This is the equation you can use to look for specific volume nu if you have a mixture. And same equation applies. How do we look for U or H if you have a mixture? Same equation. Okay, so first of all, you have two components. The first one is UF, the specific internal energy of the saturated liquid. And the second component is UG, specific internal energy of the saturated vapor. And then how much do we have for the vapor? That's the definition of quality. And then how much liquid do we have? That's the rest, so 1 minus x. Same equation for H. So it's 1 minus x times HF plus x times Hg. Okay, so if you have a mixture and you're looking for nu, U, or H, you can use those equations.